scientists may have just discovered the strongest sign of alien life ever detected on a planet they once ignored completely. A distant world called K218b could be hiding living organisms beneath an ocean unlike anything on Earth. One tiny molecule is now forcing scientists to question everything we thought we knew about where life can exist in the universe. And today, we're exploring why the deeper we look into K218b, the more unsettling the truth becomes. Now, let's begin. A molecule smaller than a speck of dust, drifting through alien skies 120 light-years from Earth, just demolished 4 centuries of scientific certainty before anyone finished their morning coffee. Not a supernova, not a gamma-ray burst, not some catastrophic cosmic event that shook the foundations of physics. A molecule, one of the smallest, most unremarkable chemical structures in the known universe, a compound so ordinary that the ocean breeze carries it every time a wave breaks on a beach. And yet, when the James Webb Space Telescope detected its signature in the atmosphere of a distant planet on an otherwise forgettable Tuesday morning in December, the ripple it sent through the scientific community was unlike anything seen in living memory. 400 years ago, Galileo pointed a crude telescope at Jupiter and saw moons orbiting another world. It shattered the idea that everything in the cosmos revolved around Earth. What happened in that December data download was the next seismic shift, and it arrived not with a bang, but as a thin dip in a wavelength graph that most people wouldn't even recognize as significant. The scientific consensus for decades had been quiet, firm, and largely unchallenged. Sub-Neptune planets, worlds between the size of Earth and Neptune, are dead, uninhabitable, crushed under hydrogen atmospheres so thick and pressurized that complex chemistry simply cannot take hold. These are the most common type of planet in the Milky Way galaxy. They outnumber rocky, Earth-like worlds by a staggering margin. And for as long as exoplanet science existed as a serious discipline, they were written off, filed away, treated as background noise in the catalog of the cosmos. K218b was the perfect representative of that dismissed category. Orbiting a quiet red dwarf star in the constellation Leo, it had been logged, measured, and largely forgotten. Its mass is approximately 8.6 times that of Earth. Its atmosphere is dominated by hydrogen. Its surface, if it even has one in any conventional sense, sits beneath layers of gas and pressure that would be instantly lethal to any life form humanity has ever encountered. Nobody placed a bet on K218b. It wasn't even on the shortlist for serious biological investigation. Then Webb stared at it. Over multiple transits, the moments when K218b passes in front of its host star Webb collected photons that had been traveling through space for over a century. Light that left that distant star system when the Wright brothers were still figuring out how to keep a plane in the air for more than a few seconds. That ancient light passed through K218b's atmosphere, where different molecules absorbed different wavelengths, each leaving a faint but precise chemical fingerprint. Webb's instruments, operating at temperatures colder than the surface of Pluto, decoded those fingerprints one spectral line at a time. Water vapor appeared, then methane, then carbon dioxide. Interesting, but not earth-shattering on their own. But when the team led by astrophysicist Niku Madhusudan at Cambridge University examined the latest round of data, something stopped everyone cold. A signal sitting at a very specific wavelength, matching a very specific compound with a statistical confidence of 99.7%. Dimethyl sulfide. That is the molecule that demolished 4 centuries of assumptions. Not because it is exotic or dangerous or radioactive, because on Earth, every single place it has ever been detected, in every environment ever studied, dimethyl sulfide has exactly one source. Living organisms, marine phytoplankton, produce it in massive quantities as they decompose. Soil bacteria release it during metabolic processes. There is no volcanic reaction, no lightning-triggered chemistry, no geological mechanism that generates it in measurable concentrations. It is, in the most precise scientific language available, a biosignature. And it was floating through the sky of a planet that was never supposed to have anything at all. Here is what makes this discovery genuinely destabilizing. K218b was not discovered by accident through some lucky alignment of telescope and sky. It had been observed before, analyzed before, and categorized before, and placed in the pile of worlds not worth pursuing. It took a new instrument, operating at previously impossible sensitivity, to reveal what had been there all along. The implication sits quietly beneath the headlines. If this planet specifically flagged as unpromising, specifically belonging to a category dismissed as lifeless, is showing biological signatures at 99.7% confidence, then the question is no longer about K218b alone. How many other planets, already cataloged, already dismissed, already filed away in the dead world column, are sitting in that same pile? How many signals have passed through telescopes that simply were not built to read them? How many worlds have we looked directly at, seen nothing alarming, and moved on while something alive drifted through their skies? The universe did not change on that Tuesday morning in December. The data did not lie. The molecule did not suddenly appear. What changed was the instrument capable of noticing it, and that distinction is everything. But to understand why one small molecule caused this much disruption, it is necessary to look carefully at the thing it is in the process of breaking. The search for extraterrestrial life has always been, quietly and uncomfortably, a search for ourselves. Not consciously, not with any malicious intent, but embedded deep in the methodology, in the mission design, in the way telescope time is allocated and research funding is prioritized. There has been an assumption so foundational, it rarely gets stated out loud. Life, if it exists elsewhere, should look like life here. It should need what we need. Breathe roughly what we breathe. Require liquid water sitting on a rocky surface within a comfortable range of a sun-like star. If it fits that profile, it earns attention. If it does not, it waits. Scientists call this Earth-centric bias. The term sounds neutral, almost clinical. In practice, its consequences have been enormous. Consider the exoplanet catalog as it stood entering the era of the James Webb Space Telescope. Thousands of confirmed planets, a rich database built over decades of painstaking observation. And within that catalog, the worlds receiving the most sustained scientific attention, the ones designated as priority targets for atmospheric analysis, for potential follow-up missions, for the bulk of serious biosignature research, were rocky planets. Small, dense, Earth-sized or near-Earth-sized worlds orbiting at distances that would place liquid water on their surfaces, the so-called habitable zone around sun-like stars. Sub-Neptune planets, like K218b, were not in that conversation. They were acknowledged as common, extraordinarily common, making up a significant fraction of all known exoplanets and then systematically deprioritized. The reasoning felt airtight. Hydrogen-dominated atmospheres create crushing pressure at depth. The chemistry should collapse into simple equilibria. Nothing complex, nothing biological, could survive those conditions. Case closed. The logic was not dishonest. It was derived from everything humanity understood about life's requirements based on the only example ever studied: Earth. One data point. A single reference frame applied universally across a galaxy containing hundreds of billions of star systems. Think about what that actually means. It is the intellectual equivalent of surveying bird life by listening exclusively for bird song, concluding from the silence of penguins and ostriches that they cannot possibly be birds. The conclusion feels rational from inside the methodology. The methodology itself is the problem. K218b demonstrates this with particular clarity. Before Webb came online, the planet had already been observed by the Hubble Space Telescope and the Spitzer Space Telescope. Water vapor was detected in its atmosphere as early as 2019. That detection generated scientific interest, but did not dramatically shift how the planet was classified or how urgently it was pursued. It remained, in the working language of the field, a benchmark sub-Neptune, a useful reference object, not a candidate for biological investigation. The category it belonged to predetermined how seriously its atmospheric data was taken. This is how Earth-centric bias operates in practice. It does not require anyone to consciously dismiss a planet. It operates through the frameworks used to decide what questions are worth asking, what instruments to build, what wavelengths to prioritize, what atmospheric compounds to treat as meaningful versus coincidental. When the framework assumes life needs to resemble Earth, every departure from Earth becomes evidence against habitability rather than evidence of a different kind of habitability. The uncomfortable part is that this bias is not a failure of intelligence or rigor. It is a feature of how human cognition works. Brains categorize by pattern recognition. Pattern recognition requires a template. The only biological template available is the one built from 4 billion years of evolution on this specific planet, in this specific corner of one specific galaxy. To step outside that template requires a deliberate, sustained effort that cuts against the grain of how minds naturally organize information. Even the language used in astrobiology reflects this. The phrase habitable zone technically refers only to the range of distances where liquid water could exist on a planetary surface, but it has functionally become synonymous in many research contexts with the place where life could exist. The moment a planet falls outside that zone, or lacks a rocky surface, it falls outside the primary area of concern. Automatically, without detailed evaluation, the numbers behind this bias are striking. Sub-Neptune planets, including mini-Neptunes and the newly named Hycean worlds. Hydrogen-rich planets with potential liquid water oceans represent a substantial portion of all confirmed exoplanets discovered by missions like Kepler and TESS. Some estimates suggest that worlds in this size range outnumber rocky Earth-like planets in the galaxy by a considerable margin, if even a fraction of them harbor conditions compatible with some form of biology. The total volume of potentially inhabited space in the Milky Way increases by an order of magnitude compared to previous estimates. That fraction spent decades sitting in the do not prioritize column. What changed was not science's understanding of life. What changed was the capability of instruments. Webb's near-infrared spectrograph operates at a sensitivity that makes its predecessors look like candlelight next to stadium floodlights. For the first time, a telescope could resolve the faint chemical fingerprints of a sub-Neptune atmosphere well enough to detect trace compounds at concentrations that would have been completely invisible to any previous observatory. The window did not open because astronomers suddenly decided to look in a new direction. It opened because they finally had something powerful enough to see through it. And what was waiting on the other side had apparently been there for a very long time. There is something worth sitting with in that realization. The cognitive architecture that caused the scientific community to overlook entire categories of planets for decades is the same architecture operating in every person reading about this discovery and instinctively asking whether the life on K218b, if it exists, is anything like us. Whether it breathes, whether it sees, whether it would recognize us as something worth communicating with. These are deeply human questions, and they are also, by definition, deeply Earth-centric ones. The universe does not organize itself around what is intuitive to a 3-pound primate brain on a small rocky planet orbiting a mid-sized star. The fact that K218b's potential biology may involve organisms that metabolize hydrogen float through dense atmospheric layers, and have never encountered anything resembling sunlight is not an argument against calling it life. It is an argument for expanding what life is allowed to mean. The greatest obstacle to finding life beyond Earth was never the distance. It was never the technology, though the technology had to catch up. It was a quiet, persistent, entirely understandable assumption that life out there would make itself known by looking like life in here. K2-18b did not fit the template. It was never supposed to. And yet, here it is. So, what actually drove Webb to look more carefully at a planet so many had already passed over? Webb does not see. That distinction matters more than it sounds. Every telescope built before it, from Galileo's crude glass tube to Hubble's iconic mirror, operated fundamentally as a device for collecting and focusing light that human eyes could process. They extended vision. Webb does something categorically different. Its primary instruments are tuned to infrared wavelengths, a range of the electromagnetic spectrum that the human eye cannot detect at all. Calling it a telescope in the traditional sense is a bit like calling a submarine a boat. Technically related, functionally another thing entirely. What infrared sensitivity actually means is this: every object in the universe above absolute zero emits heat radiation, and that radiation carries chemical information. Molecules do not just float passively through space and atmosphere. They vibrate, they rotate, and each molecule vibrates and rotates at frequencies so specific, so precisely determined by its atomic structure, that no two compounds produce the same pattern. Water vapor has its signature, methane has its own, carbon dioxide, ammonia, dimethyl sulfide. Each one announces itself in infrared light, like a fingerprint on a glass, unambiguous, unrepeatable, waiting to be read by something sensitive enough to notice. Webb was built to notice. The technique used to analyze K2-18b's atmosphere is called transit spectroscopy, and the elegance of it is almost architectural. When K2-18b passes in front of its host star, an event called a transit, the vast majority of the star's light travels directly to Webb without interference. But a thin slice of that light clips the outermost edge of the planet's atmosphere instead of passing around it. As that light pushes through the atmospheric layers, different molecules absorb different wavelengths. By the time it reaches Webb's detectors, the light is no longer the same. It carries absence's precise gaps where specific wavelengths have been removed, each gap corresponding to a compound that grabbed those photons on their way through. Imagine holding a flashlight behind a wine glass filled with red wine. The light that reaches your eye is not white anymore. The liquid absorbed certain wavelengths and transmitted others, and the resulting color tells you something about the contents of the glass. Now imagine doing that with a glass of liquid positioned 120 light years away, and reading not just the color, but the exact molecular composition of every compound dissolved in it, at concentrations measured in parts per billion. That is transit spectroscopy. That is what Webb does every time K2-18b drifts across the face of its star. The numbers behind this process are difficult to hold in the mind comfortably. During any given transit, the fraction of photons that actually pass through K2-18b's atmosphere and carry chemical information is roughly 1 in 1 million. The overwhelming majority of the light Webb collects in those moments belongs to the star itself and carries no planetary data at all. Webb's instruments must isolate that 1 in a million signal, measure its wavelength absences with extraordinary precision, and do so consistently enough across multiple transits to distinguish genuine molecular signatures from random statistical noise. It does this reliably, routinely, even. This level of sensitivity requires an environment that borders on the extreme. Webb is positioned at the second Lagrange point, a gravitationally stable location approximately 1.5 million kilometers from Earth in the direction away from the Sun. At that distance, the combined shadow of Earth and the Sun falls across Webb's sun shield constantly, keeping the telescope in perpetual cold. The primary mirror and all scientific instruments are maintained at temperatures below -233 degrees Celsius, colder than the surface of Pluto, colder than anywhere in the solar system that sunlight can reach. That cold is not incidental. It is the entire point. Infrared detectors are heat detectors. If the telescope itself were warm, its own thermal emissions would overwhelm the faint signals it is trying to read from distant worlds. Webb's primary mirror spans 6.5 meters across, assembled from 18 hexagonal gold-coated beryllium segments aligned to tolerances measured in nanometers. The gold coating is not decorative. Gold reflects infrared light more efficiently than any other material at those temperatures, maximizing the number of photons the telescope can gather from sources billions of kilometers away. The sensitivity of the system as a whole is frequently described through an analogy that refuses to stop being astonishing. Webb can detect the heat signature of a firefly hovering at the distance of the Moon. A firefly at the Moon. This is the machine that was pointed at K218b, a $10 billion instrument built over 2 decades, launched after years of delays, unfolded in space through a sequence of 344 individual mechanisms that all had to function correctly, or the entire mission would have failed. And this machine was asked to listen to a world it could never visit, read chemistry it could never touch, and find meaning in the whisper of 1 in a million photons carrying ancient light. There is something almost philosophical about what Webb represents. It was designed by humans who will never live to see the discoveries it enables fully understood. It operates at a location no person can reach to service it. It listens to worlds that will never know it exists, decoding their atmospheric chemistry with instruments so cold and precise they function in a realm completely inaccessible to human biology. The fact that such a machine was conceived, funded, built, and successfully deployed is itself a statement about something about curiosity as a survival trait. Perhaps, or about the peculiar stubbornness of a species that refuses to accept the limits of its own senses. It is also, with apologies to the engineers who spent careers on it, slightly absurd. $10 billion to eavesdrop on planets that have no idea we are listening. To catch the chemical exhale of a world that has been breathing in silence since long before the first human civilization scratched its first symbol into clay. It is the most extravagant act of listening in the history of the species. And in December, during one unremarkable morning in one unremarkable data download, it paid off in a way nobody was fully prepared for. And on one December morning, that machine heard something nobody was prepared for. Stand at the edge of the ocean on a clear morning, right where the waves break. Breathe in that specific smell, briny, slightly sharp, carrying the faint suggestion of something organic and alive, has a name. Most people have never heard it. Dimethyl sulfide. The compound's chemical structure is straightforward 2 methyl groups attached to a single sulfur atom, written as the formula where carbon, hydrogen, and sulfur combine in a precise arrangement that organic chemistry makes routine. It is not dramatic in appearance or behavior. It does not glow or react violently or announce itself in any spectacular way. In a laboratory context, it would be considered unremarkable, a minor sulfur compound, background noise in atmospheric chemistry discussions. Except for one thing. On Earth, dimethyl sulfide has a single known origin: life, specifically marine phytoplankton, microscopic photosynthetic organisms drifting through the upper layers of the ocean, produce a precursor compound during their normal metabolic processes. When these organisms die and decompose, that precursor breaks down into dimethyl sulfide and gets released into the atmosphere. Soil bacteria generate it through different metabolic pathways. Various marine microorganisms contribute to its production throughout the global ocean. The result is a steady, measurable background concentration of the compound in Earth's atmosphere, almost entirely attributable to biological activity. No volcanic eruption produces it in any meaningful quantity. No lightning strike triggers its formation at detectable concentrations. No photochemical reaction involving sunlight and common atmospheric gases creates it at levels that would show up in spectroscopic analysis. Geologists have looked. Atmospheric chemists have looked. The non-biological production pathways for dimethyl sulfide under Earth conditions generate concentrations so low they fall beneath the threshold of measurement. For all practical purposes, if you find dimethyl sulfide, you have found biology's fingerprints. This was already well established in the scientific literature, long before Webb turned toward K218b. Dimethyl sulfide had been proposed as a potential biosignature for exoplanet atmospheres precisely because of this Earth-based exclusivity. The logic was clear: it is chemically distinctive, produced in meaningful quantities by biological processes, and absent from the non-biological chemical inventory of rocky planets and gas giants alike. If a telescope ever detected it beyond the solar system, the detection would demand serious attention. Webb detected it, not at trace concentrations, not at levels that required careful statistical massaging to pull above the noise floor, at concentrations that exceeded what any currently understood non-biological chemical mechanism operating under K2-18b's conditions could plausibly produce. The signal sat at the correct wavelength, with the correct absorption profile, repeated consistently across multiple transits. The team ran the models, they checked the noise, they looked for alternative explanations. The confidence level the analysis returned was 99.7%. In particle physics, a field with extremely demanding standards for claiming discoveries, the threshold for announcing the detection of a new fundamental particle is 99.9997% confidence, known as 5 sigma. The dimethyl sulfide detection on K218b reached 3 sigma. That is the boundary between strong evidence and definitive discovery in most scientific disciplines. In medical research, a 3 sigma result typically triggers immediate publication and significant follow-up investigation. In materials science, it would be treated as a confirmed finding. In exoplanet atmospheric chemistry, it was the strongest biosignature signal ever recorded from a world outside the solar system. The 99.7% figure is worth sitting with because it is easy to let it wash over without registering what it actually represents. It means the probability that the dimethyl sulfide detection is a statistical artifact, a random fluctuation in the data that mimics the signature of the compound, is 3 in 1,000. 3. In 1,000 attempts, the data would produce a false positive of this strength only 3 times. The other 997 times, it would mean the compound is genuinely there. This is not proof. Everyone involved in the research said so explicitly. Science does not work through single detections, however confident. Proof requires replication, independent verification, elimination of alternative explanations, and, in this case, substantially more telescope time studying K218b's atmosphere across additional transits and wavelength ranges. The researchers were careful, measured, and precise in their public statements. But there is a difference between not proof and not significant. The dimethyl sulfide signal on K218b is enormously significant. It is the kind of result that keeps atmospheric chemists awake at 3 in the morning, running the same model one more time, just to make sure the code is correct. It is the kind of number that makes experienced scientists, people who have spent careers carefully not getting excited about preliminary data, go quiet when they look at the output. If you were a scientist and you pulled up the spectral analysis on a Tuesday morning, looked at the absorption signature sitting exactly where dimethyl sulfide should sit, watched the confidence interval stabilize at 99.7% as the model converged, and understood what that compound's presence meant chemically. What would you do first? Check the data again, almost certainly. Then check it a third time. Then call someone, not because doubt was warranted, but because the human mind requires confirmation before it allows itself to believe something that large. The compound had traveled for 120 years to reach Webb's mirrors. It carried the chemical record of atmospheric processes happening on a world no human instrument had ever been able to read in this kind of detail. And in that signal, in those specific missing wavelengths in an infrared spectrum generated by ancient starlight, was the most striking suggestion yet that the chemistry of living systems is not the exclusive property of this planet. But dimethyl sulfide is only one piece of the picture. The rest of K2-18b's atmosphere is what makes the story truly impossible to explain any other way. Leave a sealed container of mixed gases alone for long enough, and something predictable happens. The reactive compounds find each other, collide, exchange electrons, and form more stable arrangements. Energy dissipates, gradients flatten. The system drifts toward the lowest available energy state, and eventually it stops changing. Chemists call this equilibrium. It is, in a sense, the chemical universe's version of settling down everything, finding its most comfortable configuration and staying there. Dead planets do exactly this. Given enough time, and planetary timescales offer enormous amounts of it, the atmosphere of a lifeless world sorts itself out. Reactive gases react with each other or with surface minerals and get locked away. Stable compounds accumulate. The ratios between different atmospheric constituents reach predictable values governed entirely by physics and thermodynamics. The whole thing goes quiet in a chemical sense, humming along in a steady state that follows from the basic properties of the molecules involved. No surprises? No deviations from what the equations predict. K2-18b's atmosphere is not doing this. It is not even close. Start with methane. In a hydrogen-rich atmosphere, at K2-18b's temperature and pressure range, methane should be present, but at concentrations determined by simple thermochemical models. The kind of calculations planetary scientists run routinely for gas giant atmospheres. Webb's measurements show methane levels significantly above what those models predict for a world operating on physics alone. Something is generating methane faster than equilibrium chemistry can account for. Something is replenishing it. Then there is carbon dioxide. Its presence in K2-18b's atmosphere at the detected concentration is, from a purely chemical standpoint, uncomfortable. Carbon dioxide can form through non-biological processes, volcanic outgassing, carbonate chemistry, but in a hydrogen-dominated atmosphere, it should react with that hydrogen under the temperatures and pressures present in K2-18b's atmospheric layers, gradually converting to other compounds. Maintaining carbon dioxide at the observed ratios over geological timescales requires an active source, something that keeps producing it. The atmosphere is holding a balance it has no obvious right to hold. And then, ammonia. This is the anomaly that most planetary scientists found the hardest to dismiss with a simple explanation. In a hydrogen-rich atmosphere, ammonia forms readily through the reaction of nitrogen, and hydrogen, it is one of the most predictable outputs of hydrogen-dominated atmospheric chemistry. Models for sub-Neptune worlds like K2-18b consistently forecast measurable ammonia concentrations. Webb looked for it. It was nearly absent. The detection sat well below the threshold that any standard abiotic atmospheric model can explain. The ammonia is missing, and the most straightforward non-biological explanation for where it went requires invoking processes that introduce more complications than they solve. 3 anomalies. 3 independent atmospheric signals, each one individually explicable through some chain of unusual geological or photochemical circumstances if you stretch the reasoning far enough. But all 3 simultaneously in a system where the dimethyl sulfide signal is already sitting at 99.7% confidence, pointing in the same direction. That is not a coincidence that gets resolved by invoking unusual geology. To understand why these 3 things together carry such weight, it helps to look at the atmosphere scientists know best. Earth's atmosphere is not in chemical equilibrium either. Oxygen and methane coexist in Earth's atmosphere right now, and their coexistence is, from a strict chemistry standpoint, unstable. The 2 compounds react with each other slowly, but persistently and without continuous replenishment. Earth's atmospheric oxygen would be consumed and its methane would be oxidized within a few million years at most. A geologically negligible blink, the atmosphere would drift toward a different equilibrium, one dominated by carbon dioxide and nitrogen. This is not happening. Both gases persist. Both maintain concentrations that should not be self-sustaining on a world operating by physics alone. The reason is simple and singular: life. Photosynthetic organisms pump oxygen into the atmosphere at a rate that outpaces consumption. Methane-producing microorganisms, methanogens living in wetlands, ocean sediments, and the digestive systems of animals continuously replace what gets oxidized. Earth's atmospheric chemistry is in disequilibrium because billions of years of biology have made it that way, and billions of organisms are working every second to keep it that way. If every living thing on Earth died simultaneously, the atmosphere would begin drifting toward equilibrium within geologically short timescales. The parallel with K218b is not speculative. It is structural. An atmosphere holding anomalously high methane, anomalously persistent carbon dioxide, and anomalously absent ammonia, while simultaneously containing dimethyl sulfide at concentrations above abiotic predictions. This is the chemical signature of a system that is being actively managed, maintained out of equilibrium by processes that continuously intervene in the natural drift toward chemical rest. In science, there is a specific moment when a hypothesis graduates into something more serious. It is not when one piece of evidence arrives. One anomaly can have one unusual explanation. It is when multiple independent lines of evidence converge on the same conclusion, when the dimethyl sulfide detection, the methane excess, the carbon dioxide persistence, and the ammonia deficit all point toward the same mechanism, that the hypothesis stops being speculative and starts being the most parsimonious explanation available, the one requiring the fewest additional assumptions, the one that fits the data without needing special pleading. 3 sigma confidence on the biosignature compound. 3 simultaneous atmospheric anomalies consistent with biological activity. No proposed non-biological mechanism that accounts for all of them without introducing implausibilities of its own. In most fields of science, this is the moment a hypothesis becomes a serious candidate for the answer. Not a confirmed answer, confirmation requires independent replication, additional observations, and systematic exclusion of remaining alternatives. But a serious candidate, the kind that gets follow-up telescope time, the kind that gets dedicated research programs, the kind that makes scientists who have spent careers carefully maintaining professional skepticism go home and find it harder than usual to think about anything else before sleep. What strikes me, and I say this genuinely, not as rhetorical ornamentation, is not that the evidence exists. It is the timing. The light-carrying K218b's atmospheric signature left that system approximately 120 years ago. It has been traveling through space for over a century, encoding the chemical state of an atmosphere that was already behaving this way before the first powered aircraft left the ground on Earth. The signal was always coming. It has been in transit for longer than most of the technology we consider modern has existed. The atmosphere of K2-18b was in disequilibrium, was doing exactly what it is doing now, while the Wright brothers were still testing engine configurations in Dayton, Ohio. We did not miss the signal because it was not there. We missed it because we had not yet built something capable of reading it. That is the part that is genuinely unsettling when you follow it to its logical end. Not the possibility of biology on K2-18b, that is extraordinary. But it is the kind of extraordinary the mind can stretch to accommodate with effort. What is harder to accommodate is the implication about every other planet already in the catalog, every sub-Neptune already measured, already filed away as uninteresting, already deprioritized because the instruments available at the time could not resolve its atmospheric chemistry to the depth Webb can. How many of those worlds have atmospheres in disequilibrium? How many of them are emitting biosignature compounds at concentrations Webb could detect? If only someone pointed it at them for long enough. The data from K2-18b did not change the universe. The universe was already this way. The evidence was already traveling. What changed was our ability to receive it. And if Webb can read this particular whisper from 120 light-years away in a planet category that was not even being seriously considered for biological investigation a decade ago, then the question of how many other whispers are already in transit, carrying chemical stories from worlds we have not yet thought to listen to, does not have a reassuring answer. The atmosphere of K2-18b has been refusing to go quiet for a very long time. It just took humanity this long to build an ear sensitive enough to notice. But to understand how life could exist there at all, it is necessary to look at K2-18b itself, a world unlike anything humanity has ever imagined. K2-18b is not Earth. It is not trying to be. And in a universe that seems to have produced it in abundance, that distinction may be precisely why it deserves more attention than anything that looks familiar. The numbers alone reframe the imagination. K2-18b's mass is approximately 8.6 times that of Earth. Its radius stretches to roughly 2.6 times Earth's. Those figures place it firmly in a category that planetary scientists have only recently begun to treat with the seriousness it warrants the Hycean world. The name is a compression of two words, hydrogen and ocean. A Hycean planet is, in the most fundamental sense, a world wrapped in a thick hydrogen-dominated atmosphere above a global liquid water ocean, with no rocky surface accessible anywhere on its exterior, no beaches, no coastlines, no continents breaking the water's surface, just ocean extending downward for distances that make Earth's deepest trenches look like puddles. Covered by a sky of hydrogen so thick and pressurized, it transitions gradually into the water below, rather than meeting it at a clean boundary. The surface temperature on K2-18b, insofar as the concept of a surface applies, is estimated at approximately 49 degrees Celsius. That is warm. Uncomfortably warm by human standards, the kind of heat that makes outdoor activity miserable and sustained exposure dangerous. But it is not a death sentence for liquid water, and it is nowhere near the threshold that eliminates complex chemistry. Under the elevated pressures present in K2-18b's atmosphere and upper ocean layers, water remains liquid across a far wider temperature range than it does at sea level on Earth. The 49-degree estimate describes the upper atmospheric conditions, not the full range of environments available within the planet's depths, where pressure and temperature create entirely different chemical landscapes. Warm at the top, a gradient of possibility below. The star K2-18b orbits is classified as an M2.5V red dwarf, a designation that tells planetary scientists a great deal about what life on any orbiting world would experience. Red dwarfs are the smallest, dimmest, and most common category of star in the Milky Way. K2-18b's host star radiates at approximately 1/30th the luminosity of the Sun. Standing on a hypothetical surface and looking up through whatever atmospheric haze existed above the star would appear as a deep crimson disk, larger than the Sun looks from Earth due to K2-18b's closer orbital distance, but radiating a fraction of the energy. The light would be dim, perpetually twilight-like by terrestrial standards, shifted heavily toward the red and infrared end of the spectrum. But here is what makes that dim, quiet star so significant for the question of life. It is going to keep burning for a duration that makes the Sun's remaining lifespan look brief. Red dwarfs of this type have estimated lifespans measured in the trillions of years, not billions, trillions. The Sun will exhaust its hydrogen fuel and expand into a red giant in approximately 5 billion years, sterilizing the inner solar system and ending any biology that remains on Earth by that point. K2-18b's host star, burning its fuel so slowly and so conservatively, will still be producing energy long after the Sun is a cooling white dwarf. Long after every Sun-like star currently visible in the night sky has completed its life cycle. In the current age of the universe, roughly 13.8 billion years old, red dwarfs like K2-18b's host have barely gotten started. The comparison is worth sitting with for a moment. The Sun is a candle burning steadily through its middle, hours warm, bright, generous with energy, but working through a finite reserve at a rate that makes its eventual exhaustion a fixed appointment on the cosmic calendar. The red dwarf orbiting at the center of K2-18b's system is an ember. Low heat, low light, but a staying power so immense it effectively decouples that world from the concept of a stellar deadline. The universe may undergo structural changes, star formation declining, galaxies dimming long before K2-18b's star runs out of fuel. What does this mean for life? Everything, potentially? The single most underappreciated requirement for biology to develop complexity is not a specific temperature or a precise chemical composition or even liquid water, though all of those matter. It is time, uninterrupted, stable, consistent time for chemistry to experiment with arrangements, for useful configurations to persist and replicate, for selection pressures to accumulate into adaptation, and for adaptation to layer upon adaptation across billions of generations. Evolution does not work on short timescales. The jump from single-celled microbes to multicellular organisms took approximately 2 billion years on Earth. The development of complex nervous systems required another several hundred million on top of that. K2-18b has been in a stable orbital configuration around a stable star for long enough that these timescales become conservative estimates rather than upper bounds. Current models suggest the system is several billion years old. The red dwarf produces relatively little ultraviolet radiation compared to Sun-like stars, reducing the intensity of the radiation environment that can damage biological molecules. There is no evidence in the available data of the kind of massive impact events that punctuated Earth's early history, resetting ecological complexity repeatedly. No record of a global glaciation locking the ocean under kilometers of ice. No equivalent of the late heavy bombardment that cratered the inner solar system's rocky worlds during their first few hundred million years. Stability is not glamorous. It does not generate dramatic headlines. But for life, stability is the most valuable resource in the universe. More important than the right chemistry, more important than proximity to energy, more important than almost any other factor that planetary scientists can measure. And K2-18b, sitting in quiet orbit around its patient ember of a star, has had stability in quantities that Earth can only gesture at with envy. But stability is only the necessary condition. The sufficient condition lies beneath the hydrogen clouds. Earth's oceans cover approximately 71% of the planet's surface. They average about 3.7 kilometers in depth. The Mariana Trench, the deepest point ever measured on this planet, reaches approximately 11 kilometers below the surface, a depth so extreme that the pressure crushes unprotected metal and the darkness is total and permanent. Humanity has visited that depth fewer times than humans have walked on the moon. K2-18b's ocean, if current models are correct, makes the Mariana Trench look like a tide pool. The planetary interior models built for Hycean worlds like K2-18b suggest a global liquid water layer that could extend to depths of several hundred kilometers before encountering a rocky core. Several hundred, not 11, not 100. A water layer so deep that if you removed Earth's entire ocean and placed it at the top of K2-18b's, it would represent a thin surface film above an abyss whose bottom lies farther down than the distance from New York to Chicago. The ocean is not a feature of K2-18b. It is most of what K2-18b is. At those depths, water does not behave the way anyone who has ever swum in a lake or ocean understands. Pressure determines the phase of matter, and pressure at the bottom of a several hundred kilometer water column is not something Earth provides any natural analog for at accessible scale. Water subjected to that kind of compression transitions into phases that do not exist anywhere in Earth's hydrosphere. Supercritical water, a state where the distinction between liquid and gas collapses and the fluid takes on properties of both, simultaneously may exist in K2-18b's intermediate depths. Deeper still, under pressures high enough to force water molecules into crystalline lattice structures, even at temperatures well above normal freezing points. The water may form what physicists call ice 7, a dense, hot form of ice that exists only under extreme compression and has no analog in any natural environment on Earth's surface. Go deeper still, and the hydrogen dissolving from the overlying atmosphere into the ocean under pressure may create exotic hydrogen water compounds whose properties have not been fully characterized because laboratory equipment capable of sustaining those conditions for extended periods barely exists. None of this means the ocean is lifeless. It may mean the opposite. Consider what happens at the interface between K2-18b's ocean and whatever rocky silicate core lies beneath it. At those depths, heat from planetary formation and ongoing radioactive decay in the core rocks drives hydrothermal activity water percolating down through fractures in the rock, superheating against hot minerals, dissolving chemical compounds, and venting back upward, carrying energy and reactive chemistry in concentrated plumes. This is not speculation about alien geology. This is standard planetary physics. Rocky cores in water-bearing worlds drive hydrothermal circulation. It happens on Earth. It almost certainly happens on Europa and Enceladus within our own solar system. There is no compelling reason it would not happen on K2-18b. And hydrothermal systems, it turns out, are among the most productive environments for life that Earth has ever produced despite receiving no sunlight whatsoever. The Lost City hydrothermal field in the Atlantic Ocean was discovered in the year 2000, roughly 750 meters below the surface, on the flank of an underwater mountain range called the Mid-Atlantic Ridge. What researchers found there restructured the boundaries of the habitable, dense communities of microorganisms thriving in complete darkness at temperatures and pressures that would have been classified as uninhabitable by the scientific consensus of just a few decades earlier. Powered entirely by a chemical reaction called serpentinization, the interaction between seawater and ultramafic rocks that generates hydrogen gas and heat as byproducts. No photosynthesis, no sunlight, no seasonal cycles, no connection to the surface world whatsoever. Just rock, water, heat, and chemistry, and the organisms that had figured out how to make a living from that combination. Lost City was not an isolated anomaly. Hydrothermal vent ecosystems have since been documented across the global ocean floor, each one a self-contained world running on chemical energy rather than solar energy. The diversity of life at these sites, bacteria, archaea, tube worms, shrimp, fish, crabs, all organized into functional ecological webs, demonstrated that sunlight is not a prerequisite for biology. It is one route to energy, not the only one. Scale Lost City, up. Place it at the base of an ocean several hundred kilometers deep, surrounding a rocky core that has been generating hydrothermal heat for several billion years, on a planet whose stable climate and patient star have allowed chemistry to operate without catastrophic interruption for timescales that dwarf Earth's own biological history. The chemical inputs, rock, water, heat, dissolved hydrogen from the overlying atmosphere are all present. The timescales are enormous. The environmental stability is exceptional. If life did not begin there under those conditions, explaining why it did not becomes the harder scientific problem. What would it look like? That is the question that is genuinely difficult to answer and genuinely worth sitting with. Organisms adapted to total darkness, immense pressure, and chemistry driven by rock-water reactions would bear no resemblance to anything that evolved under open sky and sunlight. They might process hydrogen the way Earth's aerobic organisms process oxygen, extracting energy from its chemical reactions rather than from light. They might drift through pressure gradients the way deep-sea bacteria drift through chemical gradients on Earth, sensing dissolved compounds rather than photons. Their entire sensory world would be built from chemistry and pressure, from vibration moving through dense water, from electrical gradients in the fluid. Eyes, as any Earth organism would recognize them, would be useless. Something else would take their place. If life on K218b exists in an ocean without light, without seasons, without any connection to the sky above, what does it use to navigate existence? What does it sense? What does it want? If want is even a meaningful word for what moves through those pressurized dark waters. And the answer, surprisingly, may not be as alien as the conditions suggest, because Earth has already shown us what life does when the lights go out. In the abandoned reactor buildings of Chernobyl, where radiation levels remain high enough to damage electronic equipment, and where no remediation effort has been able to make the environment safe for sustained human presence, something is growing on the walls. Not mold in the conventional sense. Radiotrophic fungi organisms that use melanin pigments to convert ionizing radiation into chemical energy, the way plants use chlorophyll to convert sunlight. They are not merely surviving in one of the most hostile human-made environments on Earth. They appear to be thriving. The radiation that killed human beings within days of the 1986 disaster is, for these organisms, a food source. In the dry valleys of Antarctica, where temperatures drop to -20 degrees Celsius and ultraviolet radiation bombards exposed surfaces with an intensity that few environments on Earth match, a fungus called cryomyces. Antarcticus lives inside translucent rocks. Not on them. Inside them, it colonizes the microscopic pore spaces within sandstone, using the rock itself as a shield against temperature extremes and radiation, extracting what little light penetrates the stone's surface, and metabolizing at rates so slow they are difficult to measure with standard equipment. Remove those rocks and examine the interior surfaces under a microscope, and there it is, alive, growing, completely indifferent to conditions that would kill most organisms within minutes. Then there is Deinococcus radiodurans, a bacterium so impervious to ionizing radiation that it has earned the informal title of the world's most radiation-resistant organism in the Guinness World Records. The lethal radiation dose for a human being is approximately 5 grays. Deinococcus radiodurans can withstand doses exceeding 1,500 times that level, roughly 7,500 grays, and resume normal cellular function afterward. Its DNA gets shattered into hundreds of fragments by that radiation exposure. The organism reassembles those fragments with extraordinary fidelity and keeps dividing. It does this not through any exotic biochemistry, but through an unusually robust DNA repair system built from the same molecular machinery that operates in every living cell on Earth. Evolution found a way. Evolution always finds a way. These are not curiosities. They are not edge cases or lucky accidents in the history of biology. They are data points in a pattern that Earth has been demonstrating consistently for the better part of 4 billion years. Wherever there is liquid water, a usable energy source, and the basic chemical building blocks of organic molecules, life appears, and once it appears, it expands into every available niche, regardless of what that niche's conditions look like to any external observer. The environments once classified as definitively uninhabitable have been reclassified, one by one, as extreme but occupied. Boiling acidic hot springs, hypersaline lakes where the salt concentration kills most cells by osmosis, Antarctic subglacial lakes sealed beneath kilometers of ice for millions of years, the interior of nuclear reactors. Every time science drew a line and said life cannot exist past this point, something was already living past it. This is not the exception to the rule of life. It is the rule of life. Apply that rule to K2-18b, and the supposedly hostile conditions begin to look like a list of solved problems rather than barriers. High-pressure environments. Elevated pressure actually stabilizes complex organic molecules by preventing their thermal degradation, increases the solubility of gases in water, making more chemical reactants available simultaneously, and forces chemical reactions that would not proceed at lower pressures. Deep-sea organisms on Earth have evolved pressure-adapted enzymes and membrane lipids that function optimally at pressures that would denature proteins in surface-dwelling species. Pressure is not inherently hostile to life. It is an environmental parameter that evolution navigates the same way it navigates temperature, pH, or salinity. Absence of sunlight. Photosynthesis is one metabolic strategy, not the definition of metabolism. Chemolithotrophs, organisms that harvest energy from inorganic chemical reactions rather than light, represent an enormous and ancient branch of life's tree. Hydrogen-eutrophic methanogens are particularly relevant here. These archaea, found in deep-sea sediments, wetlands, and the digestive tracts of various animals, generate energy and produce methane as a metabolic byproduct by combining hydrogen gas with carbon dioxide. They require no sunlight. They require no oxygen. They need hydrogen, carbon dioxide, water, and a handful of trace minerals. K2-18b's hydrogen-rich atmosphere and carbon dioxide-containing atmospheric layer, sitting above an ocean potentially rich in dissolved hydrogen, describes their preferred habitat with uncomfortable precision. Hydrogen-eutrophic methanogens would not find K2-18b hostile. They might find it comfortable. The elevated methane detected in K2-18b's atmosphere, the anomaly that contributes to the chemical disequilibrium signal, is exactly what a population of hydrogen-consuming, methane-producing microorganisms would generate if operating at scale across a global ocean. This is not a coincidence that scientists have failed to notice. It is one of the reasons the atmospheric data produces the pattern it does. Life, it turns out, is the universe's most difficult tenant. Complain all you want about the lack of oxygen, the crushing pressure, the perpetual darkness. Hand it enough energy and enough water, and it will unpack its belongings and start redecorating. It has done this on Earth in every environment that offered those two things. Regardless of everything else the environment was doing, there is no evidence that this tendency is unique to Earth. There is considerable chemical evidence, now arriving from 120 light-years away, that it may not be. What genuinely stops me, and this is not rhetorical performance, this is the honest reaction of someone who has followed this story carefully, is not the possibility that K2-18b hosts life. It is the realization that the definition of life used to evaluate that possibility has been drawn according to a single reference organism's specifications. Earth life, specifically the subset of Earth life that is visible, photosynthetic, oxygen-dependent, and surface-dwelling, which represents a thin slice of the actual biological diversity that exists on this planet. When that narrow template was applied to the rest of the universe looked mostly empty. Remove the template and look at what conditions are actually necessary rather than what conditions are familiar, and the universe begins to look like a place where the relevant question is not whether life exists elsewhere, but how many different chemical strategies it has found to persist. But if life is this adaptable, why did it take until 2025 to find the first evidence from beyond the solar system? The Hubble Space Telescope launched in 1990 and spent the following decades producing some of the most celebrated images in the history of science. Deep field exposures revealed galaxies at the edge of the observable universe. Observations of stellar nurseries showed the physical process of star formation in unprecedented detail. Hubble fundamentally changed how humanity visualizes the cosmos and contributed to discoveries that earned multiple Nobel Prizes in physics. It could not tell you whether K2-18b has methane in its atmosphere. Not reliably, not at the precision required to identify biosignature concentrations at a distance of 120 light-years. The Spitzer Space Telescope, designed specifically for infrared observation and operational from 2003 until 2020, pushed that capability further. It made the first detections of light directly from exoplanets and provided the initial evidence of water vapor in K2-18b's atmosphere in 2019. That detection was real. It was also blurry, statistically meaningful, but not chemically resolved to the degree that could identify individual trace compounds or measure their concentrations with enough precision to distinguish biological from geological origins. This is the instrument gap that defined the first 3 decades of exoplanet science. Astronomers could detect that planets existed. They could measure their sizes, their orbital periods, their rough masses. With considerable effort, they could sometimes detect the presence of major atmospheric constituents in the atmospheres of large, close-in gas giants. But the chemistry of sub-Neptune atmospheres, the kind of detailed molecular accounting that reads dimethyl sulfide concentrations and identifies chemical disequilibrium across multiple independent compounds, was simply outside what any telescope before Webb could deliver. The search for extraterrestrial life proceeded in the meantime through a different strategy. The search for extraterrestrial intelligence began in 1960 with astronomer Frank Drake pointing the Green Bank telescope at 2 nearby sun-like stars and listening for artificial radio signals. The logic was straightforward. Technological civilizations would presumably use radio for communication, and radio waves travel at the speed of light, making them an efficient long-distance carrier. If another civilization was out there and broadcasting, someone listening carefully at the right frequencies might detect the transmission. For 60 years, the answer was silence. Not a single confirmed detection. The Great Silence, as it came to be called, generated serious scientific debate about what it implied. Fermi's famous question, if the galaxy is full of life, where has everybody loomed over the entire enterprise, and various proposed answers grew increasingly elaborate. Perhaps civilizations inevitably destroy themselves. Perhaps interstellar distances make communication practically impossible. Perhaps radio is a brief technological phase that advanced civilizations move through quickly. Perhaps we are genuinely alone. The simpler answer, The one that the K218b data now presses toward forcefully is that the search was aimed at the wrong target in the wrong place using the wrong method. Consider the geometry of the situation. The galaxy contains somewhere between 200 billion and 400 billion stars. Of those, the vast majority are red dwarfs. Of the planetary systems that have been detected, sub-Neptune worlds appear with far greater frequency than rocky Earth-sized planets. If life in the galaxy is primarily microbial, which Earth's own history strongly implies, since microbial life dominated this planet for roughly 3 billion of its 4 billion years of biological history, then searching for radio signals from technological civilizations is like standing in the Amazon rainforest at midnight, sweeping a flashlight through the canopy, and concluding from the absence of elephants that the forest contains no animals. The methodology is not wrong in principle. It is catastrophically mismatched to the scale of what actually exists. Webb represents something qualitatively different from every instrument that preceded it. Its infrared sensitivity is not a modest improvement over Hubble or Spitzer. The gain in capability for the specific task of atmospheric biosignature detection in sub-Neptune atmospheres is approximately 100-fold over what was previously achievable, 100 times more sensitive. That is the difference between detecting a candle flame from the next room and detecting it from across a city. The same chemical signatures that were invisible noise in previous datasets become readable features. The implications of that sensitivity jump are still propagating through the field. Before Webb began operations, the number of exoplanets considered viable candidates for detailed atmospheric biosignature analysis numbered in the dozens, mostly large, hot gas giants orbiting close to their stars, where the signal-to-noise ratio was favorable despite the instrument's limitations. After Webb's first observing cycles produced results like the K218b analysis, the number of planets warranting serious reevaluation expanded into the thousands. Sub-Neptunes within observable distance that had been cataloged and deprioritized suddenly became active research targets. The catalog did not change. The ability to read it did. 60 years of silence from SETI, decades of exoplanet catalogs filled with worlds treated as geologically interesting but biologically irrelevant. An entire category of planet, the most common type in the galaxy, written off without the tools to evaluate it properly. The universe was not withholding the answer. The answer was traveling toward us the entire time, encoded in the atmospheric chemistry of worlds that were never supposed to matter. What changed was not the evidence. What changed was the instrument sophisticated enough to receive it. And when looking back at the full arc of that journey, a much more uncomfortable question emerges not about K218b, but about us. In the summer of 1950, Enrico Fermi sat down to lunch with colleagues at Los Alamos and asked a question that has haunted science ever since. The conversation had drifted toward the possibility of extraterrestrial civilizations, toward the sheer improbability that humanity was alone in a galaxy containing hundreds of billions of stars. Fermi listened, then set down his fork and asked, simply, where is everybody? The question was deceptively clean. If the conditions for life are common, and if life tends to produce intelligence, and if intelligence tends to produce technology, then the galaxy should be crowded with signals, artifacts, probes, or at minimum, some detectable evidence of other minds at work. The numbers seemed to demand it. The silence seemed to contradict it. That contradiction became known as the Fermi paradox, and for 70 years it generated more theories than answers. Some proposed that civilizations inevitably collapse before they can spread. Others argued that the distances between stars are simply too vast, that the universe enforces a kind of enforced solitude through geometry alone. A few suggested that advanced civilizations deliberately go quiet, withdrawing from the cosmos for reasons we cannot yet comprehend. The more elaborate the proposed solution, the more it revealed how uncomfortable the silence had become, a silence so total that it began to feel like an answer in itself. K218b does not resolve the Fermi paradox, but it does something more useful. It exposes the assumption buried inside the original question. Fermi asked where everybody was. The word everybody carries enormous weight. It assumes that the life worth finding is the kind that announces itself, that builds, broadcasts, expands, leaves marks large enough for a civilization 120 light years away to notice. It assumes, in other words, that the life worth looking for looks something like us. That assumption has a name in philosophy. It is called anthropocentrism. And the atmospheric data from K218b suggests it may have been the single most expensive intellectual mistake in the history of the search. Here is what Earth's own biology actually implies. Life on this planet first appeared approximately 3.8 billion years ago. For the overwhelming majority of that span, roughly 3 billion years, it consisted entirely of single-celled organisms. No nervous systems, no behavior, no signals of any kind that a distant telescope could plausibly interpret as intentional. Microbial mats, chemical gradients, the slow metabolic churn of ocean floors. Life at its most fundamental, doing what life does, extracting energy, reproducing, persisting. That is 3 billion years of biology that would have been completely invisible to any civilization searching for radio transmissions. Technological civilization, the kind that builds telescopes and fires radio waves into space, has existed for perhaps 1 century, not 100 million years, not 1 billion. 1 century out of 3.8 billion. If an alien instrument as capable as Webb had been pointed at Earth at any random moment in biological history, the odds of catching that 1 century window would be roughly 1 in 38 million. The rest of the time, what they would find is exactly what Webb found at K218b, chemical disequilibrium. Atmospheric gases in ratios that physics alone cannot sustain. The quiet metabolic signature of organisms that have no idea they are being observed. This reframes the Fermi paradox entirely. The question was never really, where is everybody? The question was always, where is everybody like us? And that is a vanishingly small subset of the possible. The pyramid of life, if it exists across the galaxy the way it exists on Earth, is almost entirely microbial at its base. Single-celled organisms adapted to chemical energy, to darkness, to pressure, to temperatures that would destroy complex tissue in seconds. Above that, vastly rare, comes multicellular complexity. Rarer still, nervous systems. Rarer still, tool use. And balanced at the very apex. Present for a geological eye blink. Technological civilization capable of intentional interstellar communication. To search for radio signals is to search for the apex and ignore the entire structure beneath it. What Webb detected at K218b is not the apex. It is, almost certainly, somewhere near the base. Dimethyl sulfide produced by organisms that have no concept of communication, no awareness of the telescope now reading their atmosphere, no interest in contact of any kind. If the detection holds and the statistical confidence of 99.7% is difficult to dismiss, then the galaxy's biology is almost certainly not centered on minds that broadcast. It is centered on chemistry that persists. The practical consequence of this is significant. If someone had confirmed the existence of a radio-transmitting civilization on K218b, the discovery would be staggering. It would answer definitively whether intelligence arises independently across the universe, whether technological development follows predictable paths, whether other minds exist capable of something like conversation. Those are profound questions. But a detection of microbial biosignatures answers a different question, and in some ways, a more fundamental one. It answers whether life itself not intelligence, not technology, but the basic phenomenon of self-replicating. Energy processing chemistry is a singular accident or a recurring feature of the universe. That question sits beneath every other question about extraterrestrial life. It is the foundation that everything else is built on. And for the first time, there is data pointing toward an answer. If life emerges wherever conditions allow, if the origin of life is not a miracle, but a chemical inevitability, given sufficient time and the right raw materials, then the implications for biology, for cosmology, for the entire philosophical framework humanity uses to understand its position in the universe, are far larger than any radio signal could produce. A radio signal would tell us someone else is out there thinking. Atmospheric biosignatures tell us the universe itself may be a living system, seeded with biology the way it is seeded with hydrogen abundantly, routinely, without exception. There is something almost quietly devastating about that possibility. Not devastating in the sense of threat, devastating in the sense that it requires dismantling an assumption so old and so deeply embedded that most people never noticed it was an assumption at all. The assumption that the cosmos is fundamentally inert and life is the exception that requires explanation. K2-18b does not prove that assumption wrong. The data is strong, not conclusive. More observations are needed. Confirmation from independent instruments will be required before any scientific consensus forms. But the direction the evidence points is clear enough that researchers are already treating the question differently. Not whether life might exist elsewhere, but how common the baseline conditions for it actually are. The Fermi paradox asked where everybody was. The answer K2-18b is beginning to sketch out is that everybody, in the sense Fermi imagined, may represent a tiny fraction of what life actually is. The rest, the vast, quiet, ancient, microbial rest, has been here all along. Living in atmospheres we lacked the instruments to read. In oceans, we had no way to observe. In chemical signatures, too faint for any telescope built before 2021 to detect. Finding microbes at K2-18b would not tell us we are not alone in any meaningful emotional sense. It would tell us something more disorienting than that. It would tell us that aloneness was never the right frame, that the universe has been running biology as a default setting for billions of years, and that we, with our radio dishes and our paradoxes and our century of searching for minds like our own, may have been looking for the rarest thing in a cosmos already full of the ordinary version. Finding microbial life at K2-18b turns out to be more important than finding a civilization, and the reason why will change how we look at the only world we have ever called home. In 1998, an economist named Robin Hanson published a paper that most people outside academic circles have never read, but whose central idea has since become one of the most quietly unsettling concepts in modern science. Hansen called it the Great Filter. The argument was straightforward, almost surgical in its logic. Somewhere between the formation of a rocky planet and the development of a spacefaring civilization, there exists a barrier so difficult to cross that virtually nothing makes it through. The universe, by all observable accounts, should be teeming with evidence of intelligence. It is not. Therefore, something stops it. Something filters it out. The question, the one that keeps certain researchers awake at genuinely inconvenient hours, is where that filter sits. There are two possibilities, and they could not be more different in their implications. The first, the filter is behind us. Life itself is extraordinarily rare. The leap from chemistry to self-replication, or from single cells to complex multicellular organisms, or from organisms to genuine cognition. One of those transitions is so improbable that almost nothing in the galaxy has ever managed it. If that is true, humanity is a near miracle. We cleared the hard part. The road ahead, while uncertain, does not include an invisible wall that has already killed everything else. The second possibility is the one no one wants to sit with too long. The filter is ahead of us. Life is common. Intelligence arises with some regularity. Civilizations develop technology, and then, consistently, reliably, across species and star systems and geological epochs, something ends them. War, resource exhaustion, climate collapse, some self-inflicted catastrophe so predictable that it functions less like a tragedy and more like a law of nature. In this version, the silence of the cosmos is not a sign that we are rare. It is a graveyard, every quiet star a monument. For decades, the Great Filter remained mostly theoretical, a philosophical puzzle dressed in astrophysical clothing. The data to test it simply did not exist. Then Webb pointed at K218b and returned a signal that changes the stakes of the question entirely. If the dimethyl sulfide detection holds, and the evidence is strong enough that the scientific community cannot casually dismiss it, then microbial life exists 120 light-years away, in an atmosphere that looks nothing like Earth's, around a star that looks nothing like the Sun, on a planet that no prior model suggested should work. That is not a marginal result. That is a data point suggesting that the origin of life is not the filter, not even close. Life, at its microbial baseline, may be something the universe does routinely. The way it makes hydrogen and helium and carbon not as an exception, but as a consequence of physical law operating over sufficient time. And that is exactly the moment when Hansen's framework becomes genuinely frightening. Because if life starts easily, the filter is not behind us. It never was. The hard part, the part that erases civilizations, lies somewhere between the first microbe and the last generation that manages to sustain a technological society without destroying the conditions that made it possible. The filter is not in the chemistry. It is in the choices. In 2024, for the first time in recorded history, the global average temperature exceeded 1.5 degrees Celsius above pre-industrial levels. That number has a particular significance. It is the threshold that the Paris Agreement identified as the boundary beyond which climate instability becomes increasingly difficult to manage, not impossible, not immediately catastrophic, but the point at which feedback loops accelerate and the margin for error narrows in ways that compound over decades. Scientists had been warning about it for 30 years. The year 2024 confirmed it had arrived. Consider what that means alongside the K218b data, a planet 120 light-years away, orbiting a red dwarf star with a fraction of the Sun's energy output, has maintained atmospheric stability for billions of years. Its chemical balance, the methane cycles, the carbon ratios, the ocean-atmosphere exchange has operated continuously, without interruption, across timescales that make human civilization look like a rounding error. That stability is not luck. It is not the product of some cosmic favoritism. It is the result of a simple fact. Nothing on K2-18b is capable of altering its own atmosphere on a timescale of 200 years. Whatever lives in those hydrogen-rich oceans, whatever drifts through that amber sky producing dimethyl sulfide and metabolizing trace gases, it does not burn fossil carbon at industrial scale. It does not reroute river systems. It does not reduce forest cover by half in a century. It persists within its environment rather than accelerating beyond it. That distinction between life that persists within its environment and life that transforms it faster than the environment can compensate may be precisely what the Great Filter is testing, not whether intelligence emerges, not whether technology develops, whether a species that gains the power to reshape its planet can refrain from doing so fatally before it learns to do so wisely. The uncomfortable reading of the K2-18b discovery is this: microbial life may be everywhere. The galaxy may be full of it. drifting through sub-Neptune atmospheres, cycling chemistry in deep oceans, persisting for billions of years on worlds that are never going to develop cities or telescopes, or the capacity for self-destruction. The filter has nothing to do with them. They clear it by default because they never reach the stage where it applies. The filter applies to us, to anything that crosses the threshold from passive biological chemistry into active technological civilization. And the question is not whether we can see it coming. The question is whether seeing it changes anything. K2-18b is stable not because it was lucky. It is stable because nothing on it has the capacity to change its atmosphere in 200 years. That observation is not a comfort. It is a mirror. But instead of only looking outward, what Webb is actually teaching us is how to understand our own home. Every model built to decode what Webb found in K2-18b's atmosphere begins in the same place, Earth. Not because the two worlds are similar, they are not. In almost any measurable sense, K2-18b is 8.5 times more massive, wrapped in hydrogen rather than nitrogen and oxygen, orbiting a dim red star at a distance that would put it inside Mercury's orbit around the Sun. The surface conditions, the ocean chemistry, the pressure gradients, essentially nothing about K2-18b resembles the planet where the scientists studying it were born. And yet, to model what is happening in that alien atmosphere, researchers must first understand, with quantitative precision, how greenhouse gases trap infrared radiation, how deep oceans absorb and release heat across centuries, how marine organisms regulate the carbon cycle from the bottom of food chains that no human eye has ever fully traced. The physics does not change between planets. The equations governing radiative transfer in a hydrogen atmosphere are derived from the same principles that govern radiative transfer in a nitrogen one. Only the parameters differ. This convergence between climate science and exoplanet science happened quietly. Without a formal announcement, there was no conference where someone stood up and declared that the two disciplines had merged. It happened because the tools required to study one turned out to be inseparable from the tools required to study the other. The same atmospheric models that simulate cloud formation in K2-18b's upper layers are refined versions of models first built to simulate cloud formation over the Pacific Ocean. The same spectroscopic databases that allow Webb's algorithms to identify methane at 120 light-years are populated with measurements taken in Earth's stratosphere by instruments that were originally designed to monitor ozone depletion. The case of dimethyl sulfide is particularly direct. When Webb's team set out to confirm the detection, they were not working from first principles. They were working from a molecular absorption database assembled over decades of Earth atmospheric chemistry research measurements of how dimethyl sulfide absorbs infrared light at specific wavelengths, taken originally because DMS is a significant factor in marine cloud formation over terrestrial oceans. The algorithm that identified the compound's spectral fingerprint in K2-18b's data had been trained, essentially, on Earth's own biology. The telescope pointed outward. The reference library pointed inward. Same equations, same models, different input parameters. There is a practical consequence to this that rarely gets discussed in coverage of the discovery. Every time researchers refine their understanding of K2-18b's atmospheric chemistry, they are simultaneously stress testing their understanding of Earth's. When a model fails to reproduce the observed methane ratios at K2-18b without invoking biological sources, that failure sharpens the model itself, which then gets applied back to Earth's methane budget, to ocean-atmosphere carbon exchange, to the feedback mechanisms that determine how quickly a disrupted climate system can or cannot stabilize. The knowledge flows in both directions. Studying a living planet 120 light-years away makes the science of studying the living planet we are standing on more rigorous, which raises a question that is harder to answer than it might initially appear. If we understand K218b's atmosphere well enough to identify biological activity, if we can read the chemical disequilibrium, detect the trace biosignatures, model the ocean-atmosphere coupling, do we understand Earth's atmosphere well enough to keep it stable? The instrumentation exists. The physics is known. The models, imperfect but functional, have been running for decades. Understanding is not the constraint. The data has been telling the same story for 30 years, with increasing clarity and decreasing uncertainty. The gap is not in the science. The gap is somewhere else entirely. There is something genuinely ironic about the position humanity currently occupies. We have built an instrument of sufficient precision to detect a biologically produced molecule in the atmosphere of a world more than 1 trillion kilometers away. To read the chemical signature of life in a place so remote that the light carrying that signature left before the Wright brothers made their first flight. We pointed that instrument at the right target, ran the right analysis, interpreted the results with appropriate rigor, and arrived at a conclusion that is statistically robust and scientifically significant. We are, by any reasonable measure, extraordinarily good at this. And yet the atmosphere of the planet where that instrument was designed, assembled, launched, and operated the atmosphere of the only world we have ever lived on continues to shift in directions that the same science, using the same methods, has been documenting and projecting and warning about for decades. It is, to put it plainly, somewhat absurd that humanity had to point a $10 billion telescope at a star 120 light-years away to practice taking its own atmosphere seriously. The telescope faces outward. The lesson lands here, and while we are still learning it, the next generation of instruments is already prepared to push the boundary further still. Webb did it one planet at a time. That is not a criticism. It is simply the arithmetic of what the telescope was built to do. Each transit observation requires hours of data collection. Each atmospheric analysis demands months of processing. Each confirmation cycle needs independent review before anyone publishes anything. For a single target, like K218b, that process took years from first observation to the dimethyl sulfide result. The telescope has revolutionized the field. It has also revealed, by doing so, exactly how slow the revolution is moving. The instruments coming next were designed with that bottleneck in mind. The Atmospheric Remote Sensing Infrared Exoplanet. Large survey mission, developed by the European Space Agency and scheduled for launch in 2029, operates on a fundamentally different philosophy than Webb. Where Webb studies one atmosphere with extraordinary depth, Ariel studies many atmospheres with systematic breadth. Its target list runs to approximately 1,000 exoplanets, 1,000 worlds whose atmospheric compositions will be characterized, compared, and cataloged within a single mission framework. The science it produces will not be the kind of singular, paradigm-shifting detection that K218b delivered. It will be something in some ways more valuable, a population-level dataset. For the first time, researchers will be able to ask not just whether one planet has unusual chemistry, but whether atmospheric biosignatures cluster around particular stellar types, particular orbital configurations, particular planetary sizes. Whether K218b is a curiosity or a pattern. Patterns are where understanding actually lives. While Ariel builds the catalog in orbit, a different instrument is taking shape on the ground. The Extremely Large Telescope, under construction at Cerro Armazones in Chile and scheduled for completion around 2028, carries a primary mirror 39 meters across. To put that in physical terms, the mirror surface area exceeds that of any existing telescope by a factor of roughly 13. That size translates directly into light gathering power, and light gathering power translates into something Ariel and even Webb cannot deliver: isotopic analysis, of exoplanetary atmospheres. Isotopes are variants of the same element, carrying different numbers of neutrons: carbon-12 and carbon-13, oxygen-16 and oxygen-18. In Earth's atmosphere, biological processes produce measurable shifts in the ratio of these isotopes. Life preferentially processes lighter variants, leaving a chemical signature in the ratios that persists even when the specific molecules have broken down. Geological processes produce different isotopic ratios. The distinction is not always large, but it is consistent, and it is real. The Extremely Large Telescope will be capable of detecting those ratio differences in the atmospheres of nearby exoplanets, essentially performing from the ground at a distance of dozens of light years, the kind of isotopic analysis that on Earth requires a laboratory spectrometer and a physical sample. It will not just identify what molecules are present, it will identify where those molecules came from, biological or geological. The question Webb could only approach statistically, the Extremely Large Telescope may be able to answer directly. The Nancy Grace Roman Space Telescope, scheduled for launch in 2027, addresses a different constraint entirely. Both Webb and Ariel require targets specific planets, already identified, already characterized well enough to justify observation time. Roman's role is to generate the next generation of that target list. Its wide-field infrared survey capability will map the galaxy with a coverage area roughly 100 times broader than Hubble's, identifying millions of new planetary candidates in timescales that previous surveys could not approach. The world's Webb and Ariel will eventually study in detail are, in many cases, worlds Roman will discover first. It is the prospector before the assayers arrive. Beyond orbiting telescopes and ground-based observatories, a more radical concept has been under serious theoretical development for years. The sun itself, it turns out, is a lens. General relativity predicts, and observations have confirmed, that mass bends light passing near it. For an object as massive as the sun, the gravitational focusing effect becomes significant at distances beyond approximately 550 astronomical units from the solar center. A probe positioned at that distance, on the far side of the sun from a target like K218b, could use the sun's gravitational field as a natural telescope of staggering magnifying power. The amplification factor at those distances would be sufficient, in principle, to resolve surface features on a planet 120 light-years away. Not atmospheric signatures, not spectral fingerprints, actual surface features, ocean boundaries, if they exist, continent-scale structures, if they exist, weather systems, if they persist long enough to observe. The engineering challenges are considerable. 550 astronomical units is roughly 17 times the distance to Pluto, and no spacecraft has traveled that far from the sun. Transit times with current propulsion technology run into decades. But the physics is sound, the calculations are done, and the concept is not fantasy. It is an engineering problem with a theoretical solution, waiting for the propulsion technology to close the gap. Within 20 years, the list of planets carrying credible biosignature candidates will no longer stand at one. It will number in the dozens, possibly in the hundreds. Once Ariel's catalog matures and the Extremely Large Telescope begins isotopic confirmation work, the question humanity is currently treating as a single data point, one planet, one signal, one team's analysis will become a field of comparative study with enough examples to identify real patterns. Whether biosignatures correlate with ocean worlds, whether they appear more frequently around red dwarfs than sun-like stars, whether the chemical fingerprints cluster around particular atmospheric compositions or scatter randomly across planetary types. The database does not yet exist. The instruments to build it are either already operational or under active construction? The timeline is not speculative. It is scheduled. But there is one scenario that no one in the astronomical community says out loud, the thing that would change everything more than finding life itself. Walk the scenario forward. Webb continues its observation program and accumulates additional transit data from K2-18b across the next several years. The dimethyl sulfide signal holds, strengthens even as more transits add statistical weight. Aerial launches in 2029 adds K2-18b to its early observation list, and its independent instruments return the same spectral features. The extremely large telescope comes online, points toward Leo, and performs isotopic analysis on the carbon compounds in that hydrogen-wrapped atmosphere. The ratios come back biological, not ambiguous, not merely consistent with biology, biological in the same unambiguous way that a carbon-14 assay on ancient bone distinguishes once living tissue from inert rock. At that point, denial is no longer a scientifically defensible position. The question changes. Not whether life exists at K2-18b, that debate is over. The question becomes what happens next. What does humanity do with confirmed knowledge that a biosphere exists 120 light-years away? The legal framework governing that question was written in 1967. The Outer Space Treaty, negotiated during the Cold War between the United States and the Soviet Union, with the United Kingdom as a co-signatory and eventually ratified by most spacefaring nations, established the basic rules of conduct beyond Earth's atmosphere. It prohibits placing nuclear weapons in orbit. It bars any nation from claiming sovereignty over the moon or other celestial bodies. It requires that astronauts be treated as envoys of humanity and assisted in emergencies regardless of nationality. These were serious provisions, seriously negotiated, addressing the actual concerns of two superpowers who were actively racing to put weapons platforms in space. The treaty contains no provisions whatsoever for the protection of an extraterrestrial biosphere. The concept did not exist as a policy concern in 1967. The treaty's authors were managing a geopolitical crisis. They were not imagining a future in which a private corporation might decide to send a probe toward a living world. That future is now imaginable, not imminent with current propulsion technology. A mission to K2-18b would require travel times in the range of 200,000 years, a number that places it firmly outside any near-term planning horizon. But propulsion technology is not static. Breakthrough Starshot, a privately funded research initiative, has been actively developing laser-propelled nanocraft capable of reaching a significant fraction of the speed of light. The project's stated near-term target is Alpha Centauri, 4 light-years distant. K2-18b is 30 times farther. But the same engineering principles that might send a nanocraft to Alpha Centauri in 20 years could, with sufficient scaling and development time, send one toward K2-18b in a matter of centuries rather than geological epochs. Here is the legal reality as it stands today if a private company decided to dispatch a probe toward K2-18b. No law currently in force would prohibit it. The Outer Space Treaty binds signatory nations. It does not clearly bind private entities operating under those nations' jurisdictions. And the question of how national space law extends to corporations conducting interstellar missions has never been tested because, until very recently, interstellar missions were not a practical concept requiring legal attention. The regulatory gap is not hypothetical. It is documented. Space law scholars have been writing about it for years, with limited traction in policy circles that have historically treated the problem as too distant to require urgent attention. Confirmation of life at K2-18b would make it urgent overnight. If we confirm life on K2-18b and the technology to reach it becomes available within a few centuries should humanity approach or keep its distance. The question sounds abstract until you place it against the only historical record available, the contact history of Earth itself. Every documented encounter between a technologically advanced civilization and a less developed one follows a pattern that requires no particular cynicism to observe. The pattern is consistent across continents, centuries, and cultural contexts. The outcome for the less developed party is rarely good. Disease introduced without malice, resources extracted without consent, ecosystems altered without comprehension of the consequences. The advanced civilization frequently arrives with no intention of harm and produces it anyway, because the interaction itself, the contact, the presence, the introduction of novel biological or chemical material constitutes a disruption that the less developed system has no capacity to absorb. A biosphere of microorganisms on K2-18b evolved across billions of years in a hydrogen-rich environment with zero exposure to Earth biology would represent the most extreme version of that vulnerability imaginable. A single Earth microorganism introduced into that ecosystem carried inadvertently on a probe, surviving the journey in some dormant state, could interact with K2-18b's chemistry in ways that are entirely unpredictable and potentially irreversible. We would not need to intend harm. We would simply need to arrive. Earth's history shows that every time a more developed civilization encountered a less developed one, the outcome was rarely good for the weaker side. The question is whether we are prepared to repeat that on a cosmic scale. But all of those questions assume that the K2-18b discovery is the end of the story. It is not. It is only the first page, and the next page will shatter everything that was just established. The light that Webb captured from K2-18b did not originate in the present. Light travels at a fixed speed, approximately 300,000 kilometers per second, and K2-18b sits 120 light-years from Earth. The photons that passed through that planet's atmosphere and carried its chemical fingerprints across interstellar space to rest on Webb's golden mirrors began their journey approximately 120 years ago. The spectrum showing dimethyl sulfide, the methane ratios, the carbon dioxide signatures, all of it is a snapshot of K2-18b as it existed around 1905. 1905, the year Albert Einstein published 4 papers that reshaped physics. The year that Norwegian explorer Roald Amundsen completed the first navigation of the Northwest Passage. The year that, in a handful of locations across the industrializing world, human beings were beginning to transmit something new into the atmosphere, not chemical compounds, not particulate matter, but structured electromagnetic radiation, radio waves, intentional signals encoded with information, propagating outward from the surface of Earth at the speed of light. The timing is not poetic coincidence, it is physics. In the same period that the light now carrying K2-18b's biosignature was departing that planet's atmosphere, Earth was generating its first artificial electromagnetic signals. Guglielmo Marconi had demonstrated transatlantic radio transmission in 1901. By 1905, experimental broadcasts were spreading from multiple transmitter sites across Europe and North America. The signals were weak. The technology was primitive. But the fundamental act had begun. A species on the third planet of a yellow dwarf star had started filling its local space with artificial electromagnetic patterns distinct from anything natural physics produces. Those signals travel at the speed of light. They do not degrade to zero. They weaken with distance, following the inverse square law, spreading across an ever larger sphere as they propagate outward. But they do not stop. A sufficiently sensitive receiver, positioned at the right distance, could, in principle, detect the aggregate electromagnetic leakage of a technological civilization, even when no individual signal was intended for interstellar transmission. 120 light-years. That is how far those first signals have traveled since approximately 1905. They have reached K2-18b. Not a deliberately aimed message, not a transmission crafted for alien detection with careful frequency selection and encoded mathematics. The ordinary, incidental, unintentional electromagnetic noise of a species learning to talk to itself. Radio broadcasts, radar pulses, television carriers, the accumulated leakage of a century of technological civilization spreading outward in all directions simultaneously. That noise, that accidental announcement, has been traveling for 120 years and has now washed over the system of the red dwarf star in the constellation Leo. If something exists at K2-18b, and the evidence now suggests that something does, and if that something possesses instrument sensitivity comparable to Webb's, it is receiving signals from Earth right now, not from our future, from our past, from the 1930s and 40s and 50s, from the era of early commercial radio and wartime radar networks and the first television broadcasts, from the decades when humanity had no idea it was announcing itself to the cosmos, because no one had yet seriously calculated how far those announcements might travel or what might be positioned to receive them. We are not the only observers in this story. In the exact moment that Webb is analyzing their atmosphere, they may be analyzing our signals. The asymmetry of the situation is worth sitting with. We observe K2-18b through chemistry, through the molecular fingerprints that its biology, if it exists, imprints on starlight. Whatever exists at K2-18b, if it observes us at all, observes us through a completely different channel, through the structured electromagnetic patterns that distinguish a technological civilization from a silent planet. We read their air. They hear our broadcasts. Neither party chose this exchange. Neither party announced it. It emerged from the physics of light and time and the independent decisions of two worlds that have never, by any conventional measure, been in contact. This is not a comfortable realization to hold. It dismantles something that felt settled, the sense that humanity occupies the position of observer, of analyst, of the party in possession of the telescope, and therefore of agency. That sense is an illusion produced by the scale of the instruments we have built and the smallness of the instruments we have imagined on the other end. Webb is extraordinary, but Webb is not unique in principle. Any civilization that has had 1 billion years to develop technology, in a stable environment, around a patient red dwarf star, may have capabilities that make Webb look like the radio telescope Frank Drake pointed at 2 nearby stars in 1960. Remarkable for its time, primitive by the standards of what followed. The universe is not silent. It never was. The question is not whether there is anyone out there. The question is when two worlds look toward each other in the same moment, who looks away first? That question does not have an answer yet. It may not have one for centuries. But it has replaced the old question, the one that defined the search for most of human history, the lonely, anxious, one-directional question of whether we were alone with something more unsettling and more honest. A question that acknowledges, for the first time, that the looking goes both ways, that the universe does not contain one species with telescopes, peering outward into passive silence. It may contain many, each one reading what the others cannot help but emit, each one a signal, each one without knowing it, already observed. Webb pointed outward and found a living world. The living world, it turns out, may have already found us